All right, today we're tackling, well, pretty much everything. From the stars burning in the sky to the phone in your hand, it's all connected by one single subject, chemistry. So let's dive in. So let me start with a question for you. What on earth could connect the blazing sun, the lead in a simple pencil, and the screen you're looking at right now? It sounds like a riddle, I know, but the answer is chemistry. And by the end of this, you're going to see just how deep those connections really run. Here's the game plan. We'll start with the map of everything to see how chemists even organize this huge field. Then we'll get into the different states of everything. After that, we'll see how one element can have many, many different faces. And finally, we'll explore what happens when we start getting it all mixed up. Okay, first up, the map of everything. So how do you even begin to make sense of a subject this huge? Well, think of chemistry like a giant, sprawling country. You can't explore it all at once, so you need a map. And scientists have made one by dividing it into different regions or branches. So why even bother breaking it up like this? Well, it boils down to three really important reasons. First off, chemistry is just way too big and complicated to tackle all at once. Second, these branches let scientists really zero in on specific parts of matter. And that focus, that's the key. That's what leads to those major scientific breakthroughs. And here's that map in action. You've got organic chemistry, which is all about carbon, the literal backbone of life. And that flows right into biochemistry, which looks at the chemical reactions happening inside you and me. Then there's physical chemistry, asking the big questions about how fast reactions happen. And inorganic chemistry, that covers pretty much everything else, like the stuff that makes fireworks pop. Finally, you've got analytical and environmental chemistry, which help us measure our world and figure out the impact we're having on it. Now let's shift gears to our next section, the states of everything. And we're really going to cover some ground here, from the solid rock under your feet all the way to the fiery core of a star. It's kind of obvious, but we take it for granted. It's worth pointing out that most of the stuff in our everyday lives, the things you can actually pick up and hold, it's all in the solid state. But once you leave our little planet, things change a lot. The most common state of matter in the entire universe is actually plasma. It's this super energized gas of ions and electrons. It's what's powering the sun, for sure, but it's also what's lighting up that neon sign down the street. Then you get these really cool, kind of weird, in-between states. Take liquid crystals. They're not quite a liquid, not quite a solid. And this unique hybrid state is the magic behind the screen you're probably looking at right now. And if you thought that was strange, let's talk about supercritical fluids. This is what happens when you compress something so much that the line between liquid and gas just disappears. It looks like a dense fog. This blurry state makes it an incredibly powerful solvent, perfect for kicking off chemical reactions that just wouldn't happen otherwise. Okay, on to section 3, and this one's one of my favorites. One element, many faces. We're going to focus on just a single ingredient, the element carbon, and see the completely different worlds it can build. So the magic word here is allotropes. It's just a fancy way of saying that one element can build itself into different structures. Think of it like this. You've got the same exact Lego bricks, but depending on how you snap them together, you can build a car, a house, or a spaceship. Same ingredient, different outcome. And carbon is the ultimate example of this. You've got diamond, where the atoms are locked into this super rigid, crazy hard structure. Then there's graphite, where the atoms form these slippery sheets. That's literally why it can write on paper. And then you get wild stuff like Buckminster fullerene, where the atoms form these amazing little soccer ball-shaped cages. Let's zoom in on that graphite for a second. It's made of stacks of these carbon sheets, right? That's what makes it feel slippery. The layers just slide right past each other. But what if you could peel off just one single layer? Well, you can, and what you get is graphene, a totally different material. It's unbelievably tough, flexible, and super lightweight. This one atom-thick sheet is such a game changer that people are calling it a miracle material. The mind-blowing part is that just by changing from stacked layers to a single layer, you go from pencil lead to a material that could revolutionize everything. It really shows you how a tiny change in atomic structure creates huge differences in our world. All right, for our last section, let's get messy. We're going to see what happens when we start mixing things up, exploring the solutions and mixtures that we deal with every single day.
So not all mixtures are the same, right? Take milk. It's what we call a colloid. You've got these tiny little particles of fat and protein just floating around, and they never settle out. But then, think about muddy water. That's a suspension. The dirt particles are bigger, And if you just let it sit, they'll all sink to the bottom.
Now for a question I am pretty sure we have all wondered about at some point. Why does sugar just vanish into a cup of hot tea, but sits in a sad clump at the bottom of your iced tea? The answer is all about something called solubility.
And the key is that temperature affects different materials in completely different ways. Take a look at this chart. Just follow the line for potassium nitrate, KNO3. See how it shoots straight up? The hotter the water, the more of it you can dissolve. Simple. But now, find the line for table salt, NaCl. It's almost totally flat. Heating up the water barely makes a difference.
And this isn't just a neat party trick for your tea. This exact principle is how chemists pull off one of their most powerful techniques, purification. Because some things get so much more soluble in hot water, you can use that to separate them out from all the junk. So here's how it works in practice. Think of it like a 5-step recipe. Step 1, dissolve your impure stuff in really hot water. Step 2, filter out any gunk that didn't dissolve. Step 3, and this is the magic part, let that solution cool down slowly. As it cools, the good stuff can't stay dissolved anymore, and it starts to form these perfect, pure crystals. Then you just collect them and dry them off. It's such an elegant way to clean things up on a molecular level.
So let's just step back for a second. In just a few minutes, we've jumped from the cosmic plasma firing inside of stars all the way down to a single sheet of atoms in graphene. And if there's one big takeaway, it's this. Chemistry is the fundamental story of how all this stuff connects. It's the invisible blueprint for our entire universe. Which leaves us with a final thought to chew on. If one single element, carbon, can be both the soft stuff in your pencil and a world-changing miracle material, it just makes you wonder, right? What other amazing hidden connections are out there just waiting for us to discover?